SwayamPrabha. Digital India. Educated India.
Hello and welcome everyone to this series of lectures on the modeling of multiphysics system. So in today's lecture we will pick up on the numerical methods that we have been discussing from last class. So in the last segment we had talked about linear systems. We have seen how a set of linear equations could be solved using the Jacobi method and the Gauss-Seidel method. We have also seen some numerical applications in MATLAB. In this lecture onwards, we will start with nonlinear systems and move towards ordinary differential equations, partial differential equations, and try to finish up the numerical methods. Okay, so a set of nonlinear systems or a nonlinear system itself is a function, say gx equals to hx, where either gx, either of the two functions, are nonlinear, which means that we can take an example, say sin x equals to x, where sin x is our gx and x is our hx. So in this case, sin x we can write an fx in such a way that is gx minus hx is equals to 0. So sin x minus x is equals to 0. So this is our expression, and this is a nonlinear equation. Now this nonlinear equation can be solved analytically or numerically. Since we are talking about numerical methods, we will go over two algorithms. The first is called the bisection method and second is called the Newton-Raphson method. So the bisection method, both of them are iterative processes. So the bisection method, again we take the same fx which is equals to 0. So we have a function fx. The method starts by taking two guess values, a naught and b naught. So these are our first iteration. Okay, again naught or 0, this is our iteration, this is our initial iteration, both of these, and these values are taken such that f of a naught is greater than 0 and f of b naught is less than 0. So if I draw a line of the different values of f of x and say this is 0, this value will be our f of a naught and this value will be our f of b naught. So f of a naught is positive and f of b naught is negative. Okay. Now what the method does is at a given stage, we declare m of k is an average of a of k and b of k divided by 2. Okay, so k is the kth iteration. So for the first iteration, m of 1 will be a0 plus b0 by 2, or m0 will be a0 plus b0 by 2, and so on. So in this way this will proceed. So once you have found m of k, then what we do is first there can be three situations, right? So the first situation is that f of ak is greater than 0 and f of mk is less than 0. Again let us draw a line. So the same line where this was 0 is the f of x values and we are putting different x values. This is f of a 0 say, and this is f of b 0. So your f of m is over here. Then b of k we will redefine our B of k as m of k, and we will keep the same value. So, B of k plus 1 rather, and A of k plus 1 will be equals to A of k. So, what we did in this process, the first step is that our m of k value for that given function lies in the negative side or less than 0. So, our a k value for the next iteration remains unchanged, that we will take the same a k. So, we will take a 1 equals to a 0, and we will take this m k, this value as a b of k plus 1 equals to m of k. Then we will find the new m k plus 1, and m k plus 1 will be equals to a k plus 1 plus b k plus 1 by 2. Okay, and then we iterate. The second scenario can be f b k is less than 0 and f m k is greater than 0. So, this case is, say that again this is 0, f of x, this is f of b k, this is f of a k, and this is f of m k. Now, f of m k is positive, the m value is coming to be in the positive side. In that case, we will keep the same value for the k plus 1 for b, b of k, and we will update the a k plus 1 with the m k value. Again, m k plus 1 will be equals to a k plus 1 plus b k plus 1 by 2. So, this value a k plus 1 will be equals to m of k, and b k plus 1 will be equals to b of k. So, now our loop will work between these 2 points. And so, what we are gradually doing is that we are gradually closing up our distance between the a0 b0. We are gradually getting closer and trying to converge to this point of 0. So, the third condition will be that f m of k is equals to 0 or tending to 0 to a certain value. In that case, our solution has converged. If the solution has converged, then m of k is the root or the solution. Okay. Now, this method we can check for error. So, error estimation for this method, if x star is an unknown root or is the unknown root. So, in that case, mod x star minus m of k should be less than mod b k minus mod m k, should be equals to 2 to the power of minus k mod b naught minus a naught. So, we are seeing that every time we are going half down. So, we are moving between the 2 points, but gradually converging, and each time the average of the 2 is taken, and then our one of our end points is shifted to that average point, right. So, this is the process. What we can see from this case is that the error value is always decreasing as the number of iteration is increasing. So, this method is bound to converge. So, this method will always work and is bound to converge. Okay. However, the process is slow and takes multiple iteration. The second process that we will look up is our Newton-Raphson. So, our Newton-Raphson method, again we take the same function f x equals to 0. What the method says that for a single scalar function, that is f of x equals to 0, the Newton-Raphson method fits the tangent or fits a tangent line to the point x n on the graph of f of x the intercept of the tangent to x axis is x n plus 1. Okay. So, what I wrote just now, let's draw it let's draw this on a plot. Say that we have a function like such. So, this is our f of x, this is our x, this is our 2b solution. Say our initial guess value x1 or x0 is over here. We will fit a tangent to this line. This becomes our x of 2. From this point, we will again go and locate our curve. We will again fit another tangent onto this line. Again, let's redraw our plot. So, we will fit another tangent. This intercept, this is x of 3, and we will gradually bring our system to a convergence. This is x of 4 and so on. Okay. So, what we are doing is we are fitting a tangent to our guess value. So, our initial guess value is x0. We find f x of 0. We draw a tangent. Tangent is a first derivative with respect to the variable. That tangent's intercept on the x axis we are taking as the next guess value. Then the second guess value we again find f x1. Then we again draw a tangent onto that point, that is f prime x1, and thus we proceed. Okay. So, since we are working with tangents, by Taylor series expansion, we have xn plus 1 is equals to f of xn plus xn plus 1 minus x of n f prime xn. If we rearrange these terms and we want to find x of n, this is from Taylor series, we get xn plus 1 is equals to, and we are trying to get this value to be close to 0. So, this will be xn minus f of xn by f of xn prime. Okay. So, this is our objective. We are trying to get our fx plus n plus 1 value to be 0. So, this value needs to be equals to 0, and that is our objective, that each iteration we move forward, our next value should be closer to 0. So, fx n plus 1 is 0, xn plus 1 equals to xn minus f of xn by f prime xn. Okay. This is our expression for the Newton-Raphson algorithm. Okay. This method converges quadratically. Right. So, what we are doing is that we start with a guess value. So, let us write down the method. Start with a guess value. Say x of 0. Find f x0 and f prime x0. Then x1 equals to x0 minus f of x0 f prime x0, right. Then use this x1 to find f of x1 and f prime x1. 6.4. Iterate this till f of xn is tending to 0. Okay. So, we will iterate this process till we converge. We will find an error margin. Say the error is that the norm, or that is the norm error, or the root mean square error, or the average error, mean average error. In any of the error criteria, if you could put it to 0 or bring it towards 0, that is what we would be looking for in this method. Okay, there is one catch in this method. So, a point to note, and this is one of the major fallacy of Newton reaptation. Although Newton reaptation is extremely popular method, but one of the major fallacy of this method is that f prime x of n should not be 0 at any point. So, for any guess value or for any initial value, our derivative value should not be 0, because if the derivative value becomes equals to 0, then our denominator, again xn plus 1 equals to xn minus f of xn by f prime xn, this denominator will be equals to 0, and if this becomes equals to 0, then our solution will blow up. Okay. So, we have to be very selective about our guess values. Some functions we have to be very careful how we select, because even if the first guess value does not meet this this condition that f prime xn equals to 0, but the next value that will be updated might give you that answer. Okay. So, that is one of the only issue with the Newton reaptation. Otherwise, this is one of the fastest algorithm to converge. Okay. This is an example of the bisection method. We have taken a function f of x equals to x cube minus x square plus 2. One of the roots is minus 1. Okay. So, by the bisection method we are taking two guess values a and b. Both these guess values we can see that the values are, one is positive, one is negative. So, this is the positive value, this is the negative value. If you look at the algorithm, then we start our algorithm, we take mi as ai plus bi by 2, that is a plus b by 2. We put it into the function, we get the function value output. If the fm value is greater than 0, then we take the same b value, but we substitute a. If it is less than 0, then we take the same a value and the b value is substituted, else the loop is broken. We are checking for the condition whether it has converged, and our tolerance is 10 to the power minus 6. So, this is our example. We can see how many iterations it takes. Our convergence comes to be near minus 1, that is our m value, and this is our f of m value. Okay. So, we can see that that there are some initial jumps, and eventually the system converges somewhere. We can take around 10 to 12, 10 to 15 iterations are taken for the convergence of this method. Okay. Compare this to the Newton reaptation. Again, the same function f of x equals to x cube minus x square plus 2. We start with the guess value, that is 0.5. This is our initial guess. First thing to check is whether our derivative is 0 or not. We can check this by substituting minus 0.5 into our fd. So, f prime x will be equals to 3x square minus 2x, that is what we did. So, we have x cube minus x square plus 2, 3x square minus 2x. Now, we will substitute our values in here. Xi plus 1 is x of I, f of xi, fd of xi. Function I plus 1 is equals to f of x of I plus 1. So, what we did is we have substituted x of I again, we are re-evaluating the value, and we are checking for our tolerance. This is our tolerance. Okay. By Newton reaptation, again we are converging to minus 1, but we are converging much more quickly, somewhere in the range of 5 to 6 iterations. Okay. So, when we compared this to our bisection method, the bisection method gave us around 10 to 12 iterations to converge. Newton reaptation converged it within 5 to 6 iterations. So, it is a much faster convergence, it converges quadratically. However, the main challenge with this is that there are certain situations in which this might lead to 0. For example, if we have f of x equals to e to the power of x minus x, then f prime x is equals to e to the power of x minus 1. If you take our initial guess value as 0, in that case, that is our solution also. If you substitute into not our solution, if you take initial guess value as 0 and you substitute into these, then the first term will be 1, but the derivative will be 0, and that gives us a problem. Right. So, we need to avoid such guess values. If we are able to do that, then Newton reaptation is an excellent method to apply. Okay. Now, we have talked about a single set of nonlinear systems. If you have a system of nonlinear systems, for example, we have f x1 comma 2 is a function, is a nonlinear function, and g is x1 comma x2 is again a set of nonlinear. So, we have two functions and two variables. Okay. We can take one example and write it down over. Say x1 square plus x2 square equals to a, and say x1 exponential of minus x2 is equals to b. Okay. So x1 square plus x2 square equals to a. Say a and b are 1 in just for the sake of example. Now we have to set two sets of parallel expressions. How do we solve this? We can use Newton raption. How to do this? So now there are two equations. So let's say that we have our x is a set of x1 and x2 for an iteration n, x of n plus 1 will be x1 and x2 for the n plus 1. Our F matrix will be our F for x of n, for our x of n. These are n squares. These are not powers, these are iterations. Please do not consider them as power. It is not x to the power of n. It is xn means nth iteration or n plus 1th iteration. I am repeating again, these are not powers. And g of x of n, you put these values in. Okay, we need a derivative. So the derivative of a set of function is called a Jacobian. So the J matrix will be the derivative of the F matrix, that will be del F by del x1, del F by del x2, del G by del x1, del G by del x2. In general, if you have f1, f2, f3 to fn functions and x1, x2, x3 to xn variables, then J is equals to del f1 by del x1, del f1 by del x2, all the way to del f1 by del xn, del f2 by del x1, del f2 by del x2, all the way up to del f2 by del xn, and del fn by del x1, del fn by del x2, all the way to del fn by del xn. Okay, this is our Jacobian matrix. Now we have our Jacobian matrix in hand. So what do? We have our x for the n plus 1th iteration equals to x for the nth iteration minus the Jacobian inverse into our function. Okay, so this is what we have done over here. We have taken two guess values for x1 and x2. We have said that we will store the last value into some. Then we have taken an error counter and we have taken an iteration counter. Okay, now we are starting our while loop for our Newton raption. We have defined our f. So f is x1 square plus x2 square minus 1, f1 square plus 2 square minus 1, and the second g is x1 exponential of minus x2 minus 1. Fx and gx both should be equals to 0. So we have to organize our terms accordingly. Then the derivative matrix will be, this is 2 cross 1, then this should be 2 cross 2. So this is you take the first expression and you differentiate with respect to x1. So 2x1 for the first one, then the derivative with respect to the second variable, so then 2x2. Again for this next expression, you take the derivative with respect to the first variable, that is exponential of minus x2, and then you take the derivative with respect to the second variable, that is minus x1 exponential of minus x2. So this is your Jacobian matrix. Okay, this is your function matrix, and this is your Jacobian matrix. Then you use this formula. In MATLAB, backslash is inverse of j, x equals to x of L minus j. Error, we have taken the normal error and then we are iterating. So this problem is iterated, and then this is our converged solution. So if you put 1 over here and 0 over here, that becomes equals to 1. If you put 1 over here and exponential of 0 is 1, you again get 1. So the solution, you will get an output that will be your converged solution after a certain number of iterations. Okay. Then we move on towards ordinary differential equation. So ODEs are derivatives of a function with respect to either time or with respect to position. First order ODEs are the first derivative. So a first order ODE, it is u of t equals to f of u. Now we have seen this expression of comma. This means it is du by dt is equals to f of u. So this is our first order ODE. And how many boundary conditions, initial conditions we need? Since it is a time derivative, we will have initial conditions. So our initial conditions, we will have one initial condition, that is u at time t is equals to 0 will be some value a or u0. Okay. So this is an example of an ordinary differential equation. In practice, we will have cases in which ODEs will come up based upon physics problems. Again, if you look at the basis of this course, these in which we will be solving from next lecture onwards practical physics based problem. So let's take up one such example, and we will have, say, a heat transfer problem, which is a lumped body problem. We will come back to this later when we will talk about heat transfer, but for now this is our expression, where rho is the density, Cp is the specific heat, V is the volume, dt by dt, in this we do not need partial, we can write complete derivatives, is our temperature derivative with respect to time. H is the convective coefficient, A is the cross section, A is the surface area through which convection is happening, T is again the temperature of the body, and T infinity is the ambient temperature. We can normalize this equation. Again, normalization of equation is like last time, we have talked about normalization. So we take theta or u bar equals to t minus t infinity over ti minus t infinity. So we do need an initial condition, t at 0 is equals to ti. Okay, we will also need a time and convergence factor is t by t naught. If you substitute this into our expression, we will have rho Cp V ti minus t infinity over t naught du bar by dt bar equals to minus Ha ti minus t infinity into u bar. So if you take the value of t naught is equals to rho Cp V over Ha, and you take this to the left hand side, we will see that these terms cancel out. This t naught will cancel out with the Ha and rho Cpv, and your expression will be du bar by dt bar equals to minus u bar, and your initial condition will be u bar at time t bar equals to 0 will be equals to 1. So this is your governing equation, and this is your initial condition. Okay. So this is a set of ordinary differential equation, and we need to solve this set of equation. So how do we solve this? We can approach this either by the Euler forward, that is an explicit way, or an Euler backward, that is an implicit way to solve this. So the Euler forward is also called explicit solving. Okay, so for the Euler forward, let's again take our equation dut is equals to f of u. Right. Again, by Taylor series expansion, u of xn plus 1 will be equals to u of xn plus dx into du by dx, so delta x du by dx plus second order terms and higher. Okay. So we can then rearrange these terms. So the du by dx, or let us write in terms of t, because we are using time instead of space. So this is t n plus 1 tn and dt. So du by dt therefore is equals to u of tn plus 1 minus u of tn by tn plus 1 minus tn, which is equals to un plus 1 minus un by delta t. All right. So this is our expression now. What we need to find out is our un plus 1 for the next iteration. So the un plus 1 will be equals to un plus delta t as a function of un. Okay. This is equals to f of u. Okay. So what we did is is f of u value for an implicit scheme we took the nth iteration rather than the n plus 1th iteration, right. That is the difference between our implicit scheme and our explicit scheme. Okay. So, if we take an example for this, say du t by dt is equals to minus au. Okay, so then u of n plus 1 is equals to u of n minus a u of n, right. So, you can take u of n into delta t, delta t. So, 1 minus a delta t. If you take un will likewise be equals to u of n minus 1 minus a delta t. Substitute this un into this expression, you will find u of n plus 1 equals to u of n minus 1 into 1 minus a delta t square. If you keep on repeating this, you will come to a point that u of n plus 1 will be equals to u of 1 minus a delta t to the power of n. Okay. So, what we are seeing is that each step we are multiplying 1 minus a delta t to the initial value, so that we can go to the next value, and this is how the time progresses. Okay. Now, for stability, for this method we need to check whether the method is stable or not. This 1 minus a delta t, this term needs to be less than 1 for a stable solution. Why do we need this to be less than 1? If you go back to the last slide, you can see that this term is multiplied over and is raised to the power of n. If this value is greater than 1, then your un plus 1 is going to blow out, right. We do not want the solution to blow out, we want the solution to converge. That is why 1 minus a delta t should be less than 1, or delta t should be less than 2 over a. Okay. So, with this stability condition in mind, we can then set up our Euler forward scheme. So, our Euler forward scheme is given over here. We have taken du by dt is equals to minus 10 u. So, our expression therefore will be un plus 1 will be equals to un 1 minus 10 into delta t, right. So, each step we will multiply, and that is what we have done over here. This one bracket is missing. So, each step we are adding this minus 10 term to this, and we are trying to converge. Okay, let us see that for different dt values, for different delta t values, this has converged, this has converged, this values is oscillating, and this solution is unstable. Okay. So, again this 2 over a term comes up. So, this 2 over a in this case is 0.2. For 0.2 is our oscillating case. Anything above 0.2, that is a 0.5, is going to blow up. Anything below that is going to converge. So, 0.001, 0.05, 0.1, although 0.1 converges very badly, we are not getting a good solution, but it will still converge. If you want to do this implicit, in that case, our expression will slightly change. So, we will write u of n plus 1 will be equals to u of n f of u of n plus 1. So, now we are using the n plus 1th iteration rather than the nth iteration, right. Now, we do not know n plus 1 or u of n plus 1. So, what do we do is that we will make some efforts to converge all the n plus 1th terms to the left, and then make a simplified expression and then take it to the right. Okay. Let us take up one example again. So, du by dt is equals to minus a of u, the same example. So, what we have done is u of n plus 1 is equals to u of n minus a into delta t into u of n plus 1. You bring this term to the left, u of n plus 1 plus a delta t equals to u of n, u of n plus 1 is equals to u of n over 1 plus a delta t. Now, like last time, if you do this successively, you will find it is u1 1 plus a delta t to the power of n. Okay. This is unconditionally stable. Unconditionally stable means you can select any value of delta t, it will always converge because it is 1 over and it is 1 plus delta t. So, it is always more than 1. Delta t will be always positive, A is positive. In that regard, the solution will always converge. Okay. This is again the same example. We have 1 over 1 plus 10 delta t n. We can see that for all the values of delta t, although we are getting very poor solutions in the case of dt equals to 0.5, however, the solution is still converged. You are not getting a solution that is going to blow up. Okay. Now, if you have a system of linear ordinary differential equation, this case is now that we have done first order ODEs. Now, if you have more than one variable, just like a non-linear system, you have more than one variable. In the same way, we have ODEs, linear ODEs, which is more than one variable. Say an example is du by dt plus v is equals to a1, or let us say a, and dv by dt plus u is equals to b. We need two initial conditions, one for u is equals to c, v of 0 is equals to d. Okay, so this set of equations is called a system of linear ordinary differential equation. These are used in mass conservation or energy conservation. Of multiple streams. So, you can have multiple inlet streams, say you are doing a chemical reactor or a batch reactor modeling, you have multiple streams coming in of different chemicals, they are reacting and they are giving different products, those product streams are going out. So, in this case the flow rates will be dependent not only on themselves, but also on the chemical reaction. And in those regards our set of equations will be coupled. So, these are coupled equations. What I mean by coupled is that the u equation depends on v, the v equation depends on u, right, and they are two-way coupled. One-way coupling means that your u equation is dependent on v, but the v equation only depends on v and or depends on itself and does not depend on u. So, you first solve for v, then use that value to solve for u, but this is a two-way coupled system. So, coupling, so a set of equations in which variables are interdependent. Okay, so that is the meaning of coupling. Now, how do we solve this set of equations? This is a very simple analysis. These equations can be much more complex. We can solve this by three ways. The first is explicit scheme or explicit method. Now, you very well know how to break these up, un plus 1 minus un by delta t. In explicit, we will take v as from the last time step, vn equals to a, which means that un plus 1 will be equals to un plus delta t a minus vn, and then vn plus 1 minus vn over delta t plus un, again the last time step. This will be vn plus 1 will be equals to vn plus delta t b minus un. So, you use the last time step to solve for the next time step. You again need your initial conditions. So, u of 1, that u1 and v1 are known and rest others are unknown. Okay. Then you have your semi implicit or semi explicit scheme. So, you have the first expression as explicit. So, un plus 1 minus un by delta t plus v of n equals to a, which gives us un plus 1. This is the same as last time, un plus delta t a minus vn. The second expression, you use the new value of un, is just like your Gauss Seidel. So, vn plus 1 minus vn over delta t plus u of n plus 1 equals to b. So, vn plus 1 is equals to vn plus delta t b minus u of n plus 1 rather than n. Okay. This is your semi implicit. It will converge faster, it will give you a solution closer to the actual solution. And then you have your fully implicit scheme. The full implicit scheme is that you have no guesses or no dependence on the last time step. everything is on the current time step. Okay, so un plus 1 minus un by delta t plus Vn plus 1 equals to A. If you rearrange these terms, then you will have un plus 1. Again, we do not know Vn plus 1, we do not know un plus 1. We do know un, so we will use this minus un plus delta t of Vn plus 1 equals to A delta t, and then Vn plus 1 minus Vn by delta t plus un plus 1 equals to B. So, Vn plus 1 minus Vn plus delta t of un plus 1 is equals to B delta t. How to set this up? We can set this up in the form of a matrix. So, we can make a matrix, and we have two variables. So, we will break this matrix into two parts. This first part is for u and this part is for v. Okay, and so this is again u, this is v, this is u and this is v. All right, our initial conditions are known. What is our initial condition? Our initial condition was c and d. So, we will use that condition. So, this is c, this is u1, this is v1, this was c and this was d, and we will have initial condition 1 0 0 and all zeros and 0 0 and all zeros. So, 1 with u1 is equals to c, that is what I mean. Again, likewise for this 0 0 for all of this, 1 0 0 for all of this, v1 is equals to d. And the second one what we have is un plus 1, that is the second term, that is our of interest, is 1, un, that is our previous term, is minus 1, 0, all zeros, and Vn plus 1, that is our second term, is equals to delta t multiplied with delta t equals to 0. So, this is our u2, u3 all the way up to un, v2, v3 all the way up to Vn, and this part is equals to A delta t. This is B delta t. Okay. Then the next term is u0 minus 1 0 all the way to 0 0 0 delta t to 0. Likewise for this is 0 delta t is with this un plus 1 and all the terms are 0. This is again minus 1 1 0 0 and same, you shift it one step is 0 0 minus 1 1 0 and so on. Okay. So, this is how you set up this matrix. Once this matrix is set up, then you can just invert the matrix and you can get all the solutions together. Okay. So, these are our schemes which is given. This is implicit, explicit and semi implicit. We can see that the values are more or less similar for the two equations and for the two expression. What we are getting is that our semi implicit values is coming around 0.661 or 62. This is coming somewhere around 0.48 or 0.5 and this is coming around 0.6. Okay. So, semi implicit is closer to implicit, explicit is slightly off. So, it depends on if you want to make explicit more accurate, you have to minimize your time stepping, that is you have to make your dt smaller. Okay. If you want to solve second order ordinary differential equations, then you have to do the second order derivative with respect to Taylor series. So, if you take this, the first order derivative we have already done, fx plus h equals to f of x plus h f prime x, or f prime x is equals to f of x plus h minus f of x over h, that is for a given f of n plus 1 minus f of n by delta x. Okay. Second order derivatives can be found from the first two derivatives. If you add these two terms together, then your first order derivatives cancel out and you will have f of x plus h plus f of x minus h, is that term is missing, plus h square f double prime x. Okay. Or f double prime x is equals to f of x plus h minus 2 f of x as f of x minus h divided by h square. Okay. This can be written as f double prime x equals to f n plus 1 minus 2 f n plus f n minus 1 by delta x square. Okay, so the next point, the central point and the last point you take, so the central point minus 2 times the right hand side point minus 2 times the central point plus the left hand side point divided by delta x square. Okay. So since you have these derivatives done, again if you want to have the first order derivative to second order accuracy, you just subtract these two terms. So you will have f of x plus h minus f of x minus h divided by h, it will be equals to f prime x 2h. Okay. So f of f prime x is also equals to f of n plus 1 minus f of n minus 1 by 2 delta x. Keep in mind that this is first order accurate, this is second order, these are all second order accurate. Okay. So any differential equation you can have say d square y u by dx square plus a1 du by dx plus a2 of u is equals to a3. Then you can discretize this equation as u of I plus 1 minus 2 u of I plus u of I minus 1 by delta x square. This is a1 times u of I plus 1 minus u of I minus 1 by 2 delta x plus a2 u of I equals to a3. This is our discretized expression. You need two boundary values. So, two boundary values are needed. What are those? So, you can have either u of 0 is equals to some constant c and u of L at the other end as some constant d. These are called Dirichlet boundary condition. You could have, say I am just keeping the first one as same and just we are changing the second one, du by dx of L equals to E. This is called Neumann. And if you have du by dx of L is A times u of L plus B, this is called Robin. So, these are the three types of boundary conditions that you can have. These boundary conditions you can express again that u of x is equals to 0 at that point is equals to 0, of x is equals to L value that is equals to d. First order derivatives, so u of x is equals to L minus u of x is equals to L minus 1 by delta x equals to E, and then u of x equals to L minus u of L minus 1 by delta x equals to A u of L plus B. Okay, so you can then simplify these expressions. Using these, what you can do is you can either do an implicit or an explicit method. In explicit method, you take a set of guess values and then based on those guess values you can solve. In this case, you will have to iterate till convergence. So, you say that you define u as some say zeros or 0.5, then set this expression up. Our interest is this is what we want to find, u of I is known, this is our interest, this is our unknown. So, you want to, the unknown part you take from the guess value, you solve everything based upon the boundary conditions and then you iterate again. So, you have now a new set of guess values, use those guess values to again repeat this iteration till you converge. Okay. Partial differential equations, we will start, we have three kinds of partial differential equation. We have parabolic, del u by del t is del square u by del x square, it's parabolic. We will have elliptic, del square u by del x square plus del square u by del y square equals to some constant a, and we can have hyperbolic. Okay, del u by del t equals to del u by del x or something in that range, or del square u by del t square, some wave equation, so del square u by del x square, right, some form of wave equation. So, parabolic equation is mostly for heat dissipation. Elliptic expressions are mostly for convergence for steady state problem, our Laplacian problems, and hyperbolic equation is mostly for waves. So, parabolic is diffusion, heat transfer, mass transfer, elliptic is convergence of steady state solutions for these, and hyperbolic is for the transient wave propagations. Okay. These equations you can solve if you can discretize. So, we will just do parabolic for this segment, and I will introduce you to others as we go forward in the class. Say del u by del t equals to del square u by del x square. So, we need one initial condition, that is u at x comma 0 is equals to some a, and we need two boundary conditions, say u of 0 comma time t is equals to b, and say you have du by del u by del x at some value L comma time t is equals to c. So, we have one Dirichlet condition, one Neumann condition, and this is our governing equation. So, you can then break up this governing equation as u n plus 1 at ith location, n at ith location by delta t equals to u of n. This is again an implicit way to do this, I plus 1 u n I plus u n I minus 1. We have done this in the last segment. So, this is our unknown, and rest everything is known. Okay. So, let us see in a graphical format. So, our bottom row is our initial condition, our left side and our right side are our boundary conditions, and these are known. Okay. So, these are well known. This is our equation that we are trying to solve. So, how do we discretize this? T n plus 1 at I minus T n at I over delta t is equals to alpha T n at the I plus 1 minus 2 T n at I plus T n at I minus 1 by delta x square plus q v. Okay. To solve this, we are just solving for this. Say this is our point T n I plus 1. What do we need? T n of I, that is this value, I plus 1 is this value, I minus 1 is this value. So, we just need the lower step time step values to solve the upper time step, and we use this. We will just keep this to the LHS and take everything else to the RHS, and we will solve. We have our boundary conditions we will need to fix. Again, we have a stability for this. Stability is that alpha delta t by delta x square should be less than 1 by 2. Okay, if this value becomes greater than 1 by 2, it is going to blow up. If it is equals to 1 by 2, it is going to oscillate, just like we have seen for our Euler forward. Okay. Boundary conditions, again we are taking a Dirichlet type and a Neumann type. We have discussed this in the former slides. What do we write is that t at this end, so t at all x at time 0 is equals to t naught. This is defined. So, everything is t naught at the lowermost step. Then our boundary conditions, t 1 comma all j values, or for different j values, say this is j and this is I, or this is n and I. So, let us just take n instead of j, since we are using this convention. T naught at a given n is equals to t naught, and t at the last one of this, say this is end comma n minus k minus t of end minus 1 of n divided by delta t is equals to 0. So, we are solving for this expression. Which time step are we taking? We are taking this time step. Say if this is n plus 1th time step, so then these will be n plus 1, n plus 1 and n plus 1. Okay. So, boundary conditions are solved after we solve the governing equation. First step, you solve this governing equation, you make up T n plus 1 of I is equals to T n of I plus alpha delta t by delta x square, T n of I plus 1 minus 2 T n of I plus T n of I minus 1 plus q v into delta t. Okay. You can see that this is solved iteratively. So, you put it into a space loop which is nested in a time loop. So, you have a time loop, then you have a space loop, and then you are solving. At the end of the space loop, you have solved from I is equals to 2 to end minus 1. Then you are solving for the boundary conditions. The boundary conditions, you will then do the T1 and T end. You will find this based upon this value, and that is how you will finish that time step, that is n plus 1th time step. Then you go to the n plus 2th time step and you use the n plus 1th time step values to proceed. Okay, let us see an example. This might be a little bit confusing for those who are unfamiliar. Okay, so we have defined t as a set of time and position steps. then we are, this is our time loop, this is our position loop. Position loop is starting from 2 to end minus 1. Time loop is starting from the second time step to end to the last time step, because we have know the initial condition. We have set it up likewise, dt by dx square alpha is equals to 1 in this case. Okay, once this is done, then we are setting up our boundary conditions. So, our boundary conditions likewise are defined. T at the left hand side is 0, T at the right hand side is constant flux. Okay, and then we are plotting. So, this is our plot, this is our time direction. So, time forward, and we can see that the temperature is increasing with time due to the heat that is being present. Same thing you can do implicit. In the implicit case, only thing is that everything on the right hand side is unknown on this term. This is known and this is known. So, you will bring this term to the left and then we will solve. We will again set up a matrix. This is called a tridiagonal matrix. We will set up a matrix containing your u n plus 1, I plus 1, I and I minus 1th term, and then we will try to converge. Again, this is unconditionally stable. We will just skip over this slide. And so, this is an example. We have set up our tridiagonal matrix over here, minus a, 1 plus 2a and a. What is a? A value is defined as dt by dx square. Where does this come from? If you go up a few slides, so this is dt by dx square, this value is a. You set up this matrix, you just invert the matrix as a matrix inversion, and then you will you solve, and you can see that you are again having the time forward the same expression you get out from Euler implicit. Try up this code in MATLAB and see how it works. If you want to see the stability, you can see the stability values for different dt values. If you increase the dt value, your Euler explicit is going to explode. However, Euler implicit will still be stable. Okay. Elliptic equations likewise are a set of two second order ordinary differential equations. So, you can now use your understood or learnt values of Jacobian Gauss-Seidel method in a second order. So, for example, this is our discretization for x and y. This is known, this is known, this is what we are interested in, this is known, again of interest and again known. These values are unknown. So, for the unknown values you can take a guess value and then you can solve based upon the guess value, that is called our Jacobi method. In the Gauss-Seidel method you take a guess value, but if you updated that value, you use the updated value, that is called the Gauss-Seidel method. So, in both cases you will attain convergence. Jacobi method will be slower, Gauss-Seidel will be faster. Try it out, it will be very similar to your linear systems problem. With that, we will finish up our lecture on the numerical methods, and from next lecture we will start up on the single physics based problems. So, heat transfer, mass transfer, solid mechanics, fluid mechanics, electromagnetism and electrochemistry. Thank you for listening to the lecture today. Thank you.